Flip-flop or bimodal jitter. A flip-flop is an electronic circuit whose output voltage has two states. When the output voltage is high, it is called state 1. When the output voltage is low, it's called state 0. This circuit is at the heart of digital computers, which rely on binary arithmetics and binary logics for the hardware and software that we use. In sfemg, the flip-flop describes two distinct values of the interpotential interval. Hence, this is called the bimodal jitter. The reason for this phenomenon, that we also see in normal muscle in 1 to 5% of the recordings, is not known. It is, however, very important to recognize, since undetected it may be misinterpreted as a recording with increased jitter. In this example, we have a pair of time-locked action potentials. We are triggering on the first potential, and the second occurs most of the time with an interpotential interval of about 400 microseconds. The jitter is normal and shows only slight variation in the IPI. But on the few discharges, the second potential jumps to the left and gives a shorter IPI. In this position, we also have a good superimposition, suggesting normal jitter also here. In this recording, we have only a few discharges of the short intervals, and it is not possible to measure jitter accurately. Using IPIs from both positions can give rise to a misinterpretation as a high jitter. Hence, jitter computation should be performed using only one of the positions. When the IPI shortens, one can hear the characteristic sound. Let us observe this phenomenon and listen to the sound of the flip-flop. Here are 5 sweeps in Raster mode. Note the interpotential interval shortened from roughly 425 microseconds to only 205 microseconds on the 4th trace. Because of the short interpotential interval, we measured the jitter using the peaks of the potential. The sequential IPI plot shows a very tight distribution of IPIs with 3 very short values. The jitter is 15 microseconds. When we exclude the short IPIs from one position, the jitter decreased by almost 50%, and now it is only 8 microseconds. In this recording we have 3 time-locked potentials. The first spike has actually 2 muscle fiber action potentials superimposed, and they occur very synchronous, and hence they often look like a single potential. But in a few discharges, the IPI becomes longer, and we observe the different shape of the first spike. It has a shoulder on its rising edge, and the peak-to-peak amplitude is reduced. Observe this sudden change in the shape of the first potential and the associated sound in the recording. The other spikes are unchanged in shape, but both show a shift in latency, a flip-flop, due to the changes in the triggering potential. Here are the sweeps in raster mode. Note the two shapes of the first spike. It is not possible to measure the jitter between the two action potentials that compose the first spike. The jitter between the first and the apparent second spike was measured. The sequential IPI plot does not show a good bimodal distribution. The jitter is 36, which is within normal limits, but we know that this is an exaggeration of what it really should be. There are some explanations for the sudden shortening of the IPI, and this is described on pages 75 to 77 in chapter 6 of the single fiber book.